Hello, once again, BC Calculus students. Mr. Record here. We're going to be talking about section 8.8. The topic is improper intervals. We're dealing with the Larson textbook, so this is the last section in chapter 8, or unit 14, with my students at Avon High School. And the thing about an improper interval that you're going to notice is that it seems to violate what we have learned about the fundamental theorem of calculus. Now, if you remember, when we talk about finding values of definite integrals, we have boundaries of a and b. You all know that, of course. But the fundamental theorem of calculus stipulates that the function be continuous on the closed interval a to b. With an improper interval, that may indeed not be the case. And in fact, there's really two things that make an integral improper. A definite integral will be improper if one of two things happens. The first thing, illustrated down below here, is that either one or both of the limits of integration are infinite. Maybe I shouldn't put an S there, huh? One or more of the limits of integration are infinite. So that means you have a boundary below of negative infinity and or a boundary above of positive infinity. And then the second criteria, although I'm not going to get into that criteria with this particular video, another one will address it, is if your function has a finite number of infinite discontinuities in the closed interval a to b. A great way to think about that would be the fact that you might have a location of a vertical asymptote somewhere in the middle of your boundary A and your boundary B. Integrals that possess either of these properties is what we call an improper integral. Now, what we're going to do here is move on to an example, and then I can go back and show you one or two of the screens that I just skipped over that kind of summarizes exactly what process that took place here. But I think if you follow along with this, you're going to have a pretty good understanding of how to solve some basic improper integrals. Now, from the very beginning, we've got a situation here where we're integrating 1 over x with respect to x, but we notice that our upper boundary is infinity. So that's what sets us apart from the other integrals that you've learned. So how do we take care of this? Well, if you remember, the fundamental theorem of calculus doesn't like having infinities as boundaries. So we need to make an adjustment here. So what we're going to do, I'm going to leave a little space after this equal sign, and I'm going to elect to call that upper boundary a b. Now, I know that b is not fully defined right now, but I'm going to think of b as being possibly some kind of finite value just for the moment, which means that we're fine to use our idea of the fundamental theorem of calculus. I'm going to choose to write dx over x as 1 over x dx for the moment. And then I think about how can I adjust this to allow b to become infinity. And if you think back to some earlier calculus that you learned probably long ago, that could be accomplished with the idea of a limit. You're going to take the limit as b approaches infinity. So you got to think of this as sort of a way to trick the improper interval. No, we're not really allowed to have an infinity up in this spot. So instead, we'll use a limit to allow that b value to approach infinity. And that's really the way that you're going to set up these improper intervals with the infinite boundaries. Now, from this point on, things are going to be pretty easy. By that, I mean we can go ahead and integrate our 1 over x, which of course gives us the natural log of the absolute value of x that we would evaluate from b to 1. And again, our limit is still just kind of sitting out, not doing anything yet. Not until we go ahead and evaluate our natural log of x, which would give us the natural log of, let's go ahead and say the absolute value of b for right now, and then we'll subtract the natural log, and we really don't need the absolute values around 1 since it's already positive. Hopefully you all are aware of the fact that the natural log of 1 is indeed 0. So all that we have left to do is take the limit as b approaches infinity of the natural log of b, which in a sense gives us the natural log of infinity. If you think of it like that, that's perfectly okay. And the natural log of infinity is infinity. You could think of the graph of natural log, which I could do a very, very rough sketch over here. Looks something along the lines of that. And as we grow to infinity with our value of x, we seem to grow to infinity with our value of y at the same time. Now, one thing that we want to do here is if we do have an answer in an improper integral of infinity, or for that matter, negative infinity, it's best to describe this with a special word, and that word is diverge or diverges. This improper integral diverges. And as you can see, the title of the problem indicates that that was going to be the case. Now, think of the word diverge as another way to say there really isn't an answer. And here in a little bit, I'll shed a little bit more light on exactly what this means graphically, and maybe compare this to another function. All right, let's take a look at example 2, and we see that it's just slightly different. We're integrating e to the negative x, but we do have the upper boundary of infinity, and you're given a little clue in the problem that this integral will converge. So it would be interesting to kind of take a look at the difference between the two. So if we integrate e to the negative x from 1 to infinity, once again, we want to set this up where we take the limit as b approaches infinity and rename our integral 1 to b e to the negative x. Now, I wanted to just take a moment. If you're watching this, you might be wondering, why am I choosing the letter b? It makes absolutely no difference. You really have several choices. The only values that I think you should really stay away from, the variable x, would be a bad choice to use up here. But b is typically a very common value to use because you're used to, in general, referring to the upper boundary as a b. So we're going to go ahead and integrate our e to the negative x. You want to be very careful there because a u substitution would allow your u to be negative x, and the derivative of that would be negative 1. I can write that out. It's most likely that you all are at a point where this can be done in your head. So that means we need to bring a negative 1 out in front of our integral. And that would also say we're going to now integrate e to the u. Essentially, this is our brand new integration problem, which of course is e to the u. But I'm going to go ahead and back substitute my u value of negative x in. That way I can retain the boundaries of b and 1. Again, our limit statement has yet to really do much of anything. And we go ahead and evaluate this as negative e to the negative b minus negative e to the negative 1. Of course, we can do a bit of simplifying with this. Negative e to the negative b power is the same as negative 1 over e to the positive b power. And the double negative here would create a plus, and then e to the negative 1, of course, is 1 over e. Now let's go ahead and let b become infinity. Let's let b become something very, very large. Now if we do that, what we've got right here is going to have a denominator that's going to become very large. So in a way, you'd have a negative 1 over something close to or approaching infinity, which for all intents and purposes will cause this to become 0. Then the 1 over e is nothing more than a constant. So if we add 0 and 1 over e, we do indeed get 1 over e as a result. And that being a finite value, a discrete value, 1 over e, we do converge. There is no need for you to write the word converge because it would be assumed that because you had a numerical answer, that the answer will converge. Now, one thing I would like to do, I'd like to go back and just revisit for a moment the integral that we did in example 1. And I think what would be really interesting for you to see as I end this particular discussion is what would the sketch of the graph of 1 over x look like, and what happens when we try to integrate from 1 to infinity. So I'm going to go ahead and use the TI Inspire, the Inspire CX CAS, and I'm going to go ahead and graph the fraction 1 over x, and we'll take a look at that. We really don't have to concern ourselves very much with the negative side of the y-axis, so I could adjust this a little bit, maybe just grab and focus a little bit more on what's happening in quadrant 1, perhaps. Yeah, as we indicated a moment ago, this is an integral evaluated from positive 1 to infinity that diverges. Now what that means is that if you were to try to find the area underneath this curve, it would add up and add up and add up and accumulate to the point where you can't count it anymore. It's basically an area of infinity. The area below the curve 1 over x and above the x-axis between 1 and infinity is infinity. Now, let's take a look at a slightly different graph. How about the graph of 1 over x squared? Now, if you're a student in my class, one of your assignments over the summer, before you even enter my Calculus AB course, is to fully understand the graphs of 1 over x and 1 over x squared and what they look like and what their characteristics are. I call them my basic 20 graphs. There are indeed 20 of them. Well, if I were to take this sketch, which you can see here is in red, drag this F2 up. Now, if you take a peek very quickly at this red graph, you'll notice that from 1 to infinity, it seems to lie predominantly underneath the blue graph, which would give one the idea that it perhaps has a little less area to compute from 1 to infinity. So maybe it would be a good idea for us to take a peek at this 1 over x squared and maybe find its improper integral evaluation from 1 to infinity. So let me go back to my document here, and I'm going to just insert a new page. Let's insert a blank page and set up a brand new problem for you guys to understand the relationship between 1 over x and 1 over x squared. So we're going to integrate from 1 to infinity 1 over x squared. Now again, my students, this is not in your note packet, so you can just sit and kind of follow along. Now, I'm going to set this up much the same way that I did the other problems. I will call this really a limit question with the boundaries 1 to b now. Okay. Should not be very difficult to integrate 1 over x squared. 1 over x squared integrates to become, let's see, this is kind of thinking, who am I? What am I? That could be best thought of as x to the negative 2, perhaps. Maybe it's easy to integrate me now. And I would have x to the negative 1 over negative 1, which gives us a negative 1 over x value. And we will evaluate this from b to 1 before we take our limit. And upon doing so, we would have negative 1 divided by b minus negative 1 divided by 1. If we go ahead and simplify just a little bit before taking our limit, we have negative 1 over b plus positive 1. And if we let b take the value of infinity, we would have essentially negative 1 over infinity, which is, for all intents and purposes, once again, 0, added to 1 which interestingly enough is 1, which means we converge. Very interesting. The integral of 1 over x squared from 1 to infinity converges to 1, but the integral of 1 over x from 1 to infinity diverges. And if I revisit here one last time the sketch of the graph, it probably makes a little bit of sense that the area under the red curve is smaller than the area of the blue curve, and it's small enough so that it actually has a numerical answer. Anyway, I hope this helps. Feel free to check out some of my other videos on improper intervals.